All right, welcome to another fascinating and exciting evening, well, morning for y'all with chemistry. Today, I just want to go over the lab a little bit and then do some chapter review, very kind of topical, and then go through some homework problems so that you guys can really understand it and not just get the right answers from the back or whatever, but actually really talk about the reasoning behind it that should help you kind of understand why those questions are asked the way they are. So the first thing I want to do is talk about the lab. So let me pause y'all while I pull that up. All right, so basically this, and you guys may not have looked at this yet, but this lab's called the boiling point elevation, and it is really less about the exact topic of colligative properties, although those are cool, and more about really working on you guys' lab technique. And so there's a background, read about colligative properties. So go ahead and do that, and you can just Google it and read through, figure out what it's talking about. There's only a couple of equations, okay, so it's not super math heavy. But then I want you guys to actually read and visualize the procedure that it's going to take to do this lab, and then to really have your tables prepared, kind of know what's going to go where, so that you can really focus on getting good exact measurements of the different boiling points. Okay, so you are going to be trying to find out what solute is dissolved in each of your three solutions. You're not going to know which is which. And I want you to be careful for temperatures. Hopefully I'm going to be able to find some thermometers. We were going to order some, and then Amazon wasn't going to come in and all that. But hopefully I found some electronic ones later today, and I'll get those to you. But the ones that I want, they often kind of vary between, on a boiling point, I tested on some boiling water, 212.4, and then it's reading 211.8. And so you just need to kind of be very aware that those temperatures might be fluctuating. And when you're talking about a little bit less than a degree, that may actually be the fluctuations in a boiling liquid. All right, so just be aware of that and be thinking about some things that could affect your results as you're getting these readings, okay? And part of what we're trying to get you guys to think through is how difficult it is in real life to get some of these really accurate results, okay? And when these guys are talking about millionths of a degree from Kelvin to do weird material science stuff, and that's really difficult to validate those results. And you guys are sort of experiencing that, and you will experience that in your lab. And we want to be thinking through those things so that you can, should it appeal to you at some point in your life, be a good scientist and do good scientific thinking, and also to kind of read things that are going on in the world, and really be able to analyze those and offer an analysis of, hey, is that a good scientific argument? Do we really know that based on these results? All right, so I'm working on having the rubric updated. I haven't had a chance to get that to you yet. That doesn't affect you for your lab, so that'll affect you for your lab report. I'll have it to you long before you start writing your lab report. We'll go from there. So I do want you guys to be thinking through that. Read through the results and discussion and what I'm expecting in that section. And I haven't decided if I want to ask you specific questions or not. I kind of want you guys to sort of teach me about colligative properties through your lab report. But I may add a couple of questions in there to help guide that discussion and help you guys really learn that topic. But I'll get that to you if we decide to change that. Do note that you need to have that last page of your lab report printed out and be able to fill that out as you're massing and weighing your unknowns and your watch glasses or whatever your container is for those. All right, so take a look at that before Thursday. Make sure you have any tables you might need prepared. Ms. Barron's going to check on those just to make sure that you guys have prepared like I've asked you to. So that shouldn't take you but 5 minutes to do it. So just go ahead and do that so I can give you a nice, easy daily grade for that. All right. Now I am going to go through some chapter review here so that we can really be good and ready. And I want you to maybe make a note here that at about 6 minutes, we're going to start test review because we had to swap stuff around just to accommodate everybody, make sure nobody was going to have to make up a lab. Man, that'd be rough for everybody involved. But since we swapped stuff around, that means I won't be able to review right before the test. So we will do the experiment on Thursday, and then we'll have a test on Tuesday. Okay, and I want you guys to have a good consolidated video where it kind of goes through the topics that you need to know. And so I'm going to take about 15 minutes and slide through these topics so that you guys will have somewhere to look and listen for when you're a little closer to the test. So maybe Monday night you guys could either listen to this again, or if you feel confident about it, just look through your chapters and all that. All right, so just kind of, again, I'm a little bit guided by these. I'm not exclusively guided by those, okay? But they are I think, a helpful way to think about what the main topics are. So, read through those and make sure you can do those things. The quiz should have been a really good guide to how that test is going to go. And guys, great job. Everybody did a really great job. And I asked maybe 2 or 3 people why they did better, because I don't want to just hand you guys easy grades, but I love it when y'all all prepare. And it seems like that's what happened, that you guys have really kind of gotten a little more up to speed on what you need to do well in chemistry, and I think that's great. So I hope we have, A's from here on out. So general structure and arrangement of the periodic table, basically, I'll just take you there, okay? Well, let's just go in order, all right? Mendeleev, like we talked about, who he is and what he's responsible for. Elements in the same group or column, you need to know groups and periods. Okay, almost everybody did really well on that. I had a couple of folks who, either called a column or didn't know it was called a group, or got them reversed. That happened on a couple. So just make sure you're clear about it. Make a note card so that you can say, all right, the vertical ones, and then you're associating that in your mind, and that's how those note cards, they just work almost on a subconscious level that eventually you just see it. It pops into your mind, and so that's how you are able to memorize it. And, noble gases were not known in Mendeleev's time. I asked you that on the quiz. Liable to make an appearance on the test. Haven't written it yet, not quite sure, but that's certainly fair game. Okay. A lot of those Asimov questions, those may show up, so make sure kind of just generally know those. I'm not going to ask you specific questions on those, but read back through that, make sure that you're a little bit familiar with those. Some of the basic tools that they used to learn about the elements, like the spectroscope or spectroscopy, and cesium is blue, rubidium was red. That's why they're named those. Just kind of read back through that, and maybe a bonus or something. All right, so we need to know metals, nonmetals, and metalloids. I think that was the most frequent thing missed of where the metalloids were. Okay, and you can see them. They're this different color right here, so they kind of do a little diagonal line right through there. So just make sure you're familiar with those. You know, I don't know what to tell you other than maybe memorize that. You know, I'm liable to ask you one of those. You don't have to remember anything because you know everything over here is metal, everything's over here is nonmetals, and 1, 2, 3, 4, 5, 6, 7, and what pattern they go in, and that should help you, or that should be able to give you an answer for any question I ask you about metals, nonmetals, or metalloids. All right, so be ready for that. Semiconductors, so vocabulary is still a part of this because again, you know, throughout chemistry we're learning sort of a language. We're learning how to write in that language, how to read in that language, how to reason using that language, and what all the symbols mean and what all the terms mean. That's all part of learning the language. Okay, so it's not just sort of silly, boring memory work. I mean, it may be boring memory work, but it has a purpose. Okay, you guys need to know all these. The only ones I saw as a problem were the chalcogens here. That's not quite as you know, common a usage, but it'll probably show up because again, we're really trying to make sure you guys are familiar so that when we're talking about these things, hey, here's what the halogens do. Boom, immediately in your mind: fluorine, chlorine, bromine, iodine. You know, you should end up with at the end of this year, you should have an oxidation state for those, what kind of electron configuration looks like there, what they're likely to do in a chemical reaction, you know, what are common ones that swap out. So we're going to keep talking about halogens. We're going to keep talking about alkali earth metals. Well, probably not alkali earth metals because I'll just call them group 1 elements. But the point is, we need to be knowing these terms, okay? So those as well. All right, and then atomic radius. I saw a couple of people just kind of went with my suggestion, which was to say, hey, atomic radius is the biggest here and the smallest there. Okay, I recommend you just memorize those, and then everything else falls into place. They get bigger as you go down and smaller as you go across. Okay, biggest, smallest. And again, I recommend writing anything you can on your test. So go ahead and write biggest and point and smallest and point. Okay, that way you can focus on doing critical thinking rather than just trying to remember what direction things go in. If you remember that small and big, you just say, oh, it's going towards helium, whether that's up or across. You know it's getting smaller. It's not a big deal to do that once you just mark it on there. Just so mark that fact on your test, okay? You could look through here, but this is not, you know, you don't need to memorize this or anything. You just need to know that as you go to the right towards helium, it gets smaller. And then as you go to the next row, boom, it pops up a lot bigger. And then it gets smaller again. And then the next row down, it gets bigger, and then it goes smaller. Oh, okay, so we're not worried about those tiny little, you know, irregularities here. Okay, we want general trends. We want general idea of what's going on and why. Okay, so that why we've got right here. Okay, number of subshells. That's 1, 2, 3, 4, 5. Those subshells there. Okay, and then second effect is the increasing attraction between the nucleus and electrons. I saw lots of good examples of this. Had some really excellent answers on this, and just, you know, review that and make sure you understand it, and then look at the shield effect and think through what it actually means. Okay, I don't need you to parrot this back to me. I don't need you to just memorize it and shield effect is this. Okay, my goal is to get you guys to understand what this is talking about, be able to put it in your own words, be able to explain it to somebody who doesn't understand it, or is younger than you, or has never had chemistry. Explain, you know, I read an interesting article. This is not a real conversation that would ever actually happen to anybody. But I read an interesting article about the shield effect. I don't understand what that is. Can you explain it to me? Yes, I can. All right. Electrons on the inside act like a shield to electrons on the outside as far as the attraction the protons have on them. Okay. And therefore, the protons aren't able to pull as strongly on those, and those electrons actually expand outward from the nucleus a little bit. All right, so that kind of just simple, intuitive answer is what we're going for there. Okay, you don't have to be an awesome science teacher to make an A, but that's the goal is to be able to explain it intuitively and using an example or a metaphor or something that helps people understand. So that's what I'm trying to do with y'all, and what I hope you guys are kind of working on yourself. So ionic radius, exactly what it is. If we're a +1, that means we've taken away electrons and it has shrunk. Okay, remember atomic radius is blue and ionic is yellow, so we go from blue to yellow. Okay, and if we're +1, +2, we're taking away electrons because they're negative and they're shrinking. Makes sense, okay? And then if they're -2 or -1, they are being added in. So guess what? Atomic to ionic gets bigger, okay? Metals always ionize by losing the electrons in their highest s orbital. Their diameters decrease considerably when they ionize. I'm not going to ask you specific questions like that. It might be good to know that metals always ionize by losing electrons in their highest s orbital. It's just a good fact to store in your mind, okay? May come up later in chemistry that it helps you understand a concept. Okay, you see the size right here. All right, we're going to work through some of these in a minute here. All right, so core and valence electrons. Okay. Remember, we've got the valence electrons. Electrons in the full shells are core, and in partially filled shells are called valence. That's it. Okay, that's what they are. So just know that. And so if you have a blank that shows up on your test, electrons in the full shells are blank, while ones in partially filled shells are blank. Make sure you've either made a note card or you've memorized that or whatever. Okay, so that you can fill those in without a problem. All right, he's got very helpful stuff. Read through these, internalize these so that you can really memorize more easily because you understand what you're memorizing. Okay, y'all feel free to reach out to me anytime during the weekend or on Monday when you start really gearing up and studying for this. If you have a question about a concept, I will be glad to type you an email that explains as best I can the concept or point you back towards something that we've talked about already or whatever. All right. Ionization energy, literally just know this definition, okay, and what it is. Visualize what's happening there, okay? Energy is being put in, and that electron is being pulled out with that energy from the atom, okay? We talked about that. There's more back in chapter 1, or maybe whatever chapter I started teaching y'all. Is it 2? Yeah, it's not 1. It's 2. Maybe it's even 3. Did I start on 3 with y'all? Yes. Okay, so in 3 here, quanta of energy and all that stuff. Okay. That's a good other example right there. All right. What is an electron volt? Okay. If you have to do calculations with this, you'll have this, but you won't have anything else. Okay, so if I need you to do a conversion between the two, you need to be proficient in that. Okay, conversions are not going away, but they're always the same. Okay, we'll try to work through one of those as well. Okay, an electron volt. Oh, we were also supposed to talk about angstroms. Where was that? Okay, make sure you get that. Here it is. Your angstroms right there. Okay. Make sure you know what that is. If I ask you about angstroms, I will not give you what that is. So you need to have 1/10 of a nanometer, 0.1 nanometers, okay? And you need to know that nanometers are 10 to the negative 9th meters, okay? So if I asked you and I said, you know, convert, I don't know, 6.1 kilometers to angstroms. Okay? What do you need to know? What do I expect you to know? Okay? I expect you to know that we have 6.1 kilometers. And I know that 1 kilometer is 1,000 meters. Okay? That is not unreasonable to ask you guys to know. All right? Some chemistry teachers or physics teachers or whatever ask people to memorize all the different, you know, mega, micro, nano, pico, deca, deci. I don't need you to know all those. I need you to know the basic ones. Okay? Kilometers, grams, milligrams, kilograms, micro, and nano are pretty much all we need to know. Okay? So you don't have to memorize anything new here other than you need to know that 1 meter is 10 to the 9th nanometers, and then your new knowledge comes in here, and you know that 0.1 nanometers is 1 angstrom. Okay? And then you just multiply across. All right, so this is going to be a pretty... Would we expect this to be a really big number or a really small number? Well, really big number because we know that we're already at 6,100 with just getting to meters. And then in each one of those meters is a billion nanometers. And then in each one of those nanometers is 10 angstroms. Okay, so 1 angstrom per 0.1 nanometers is the same as a 1 being down here and a 10 being up here. Okay. So we got 6.1 times 1,000 times a billion times 10. It's going to be a big number. Okay, so if you get a really small number, that means you've flipped one of these. Okay? And you need to have that kind of in your mind about what, you know, what's the reasonable range for these to be. All right? So do not be surprised if some sort of conversion like this comes up. All right? The goal of this guy, you know, he is this publishing company, the Novare. You can't even see it on here, but Novare. They say forget the cram, pass, forget cycle. Okay, that's what they want to get rid of. Okay, they want you to have this knowledge that sticks with you, and so conversions are a big part of that. Units are a big part of that, and never forgetting about density and mass and volume calculations. Never forgetting about, you know, what is an electron volt. We're not just going to memorize that and then forget about it. We're going to use it because the point is to give you the deep knowledge that sticks with you. All right? So you need to know what first and second ionization energy is. Okay? And then we're going to talk through this part right here, what electrons they lose, because we're going to work through your homework. I mean, I'm hoping you guys are already clear on this, but it may fade from your mind over the weekend, and so you can look back at this and watch this again or whatever. All right, so we're going to do some of that. And then note what oxidation states are right here. What is electron affinity? Okay, it's the opposite of ionization energy. Okay, ionization energy you put in, and an electron goes away. Electron and it doesn't disappear; it leaves that atom. All right, and then electron affinity is the energy released when you put an electron in. So one is energy in, electron out. The other one's electron in, energy out. Okay. All right, and then we have electronegativity. Measure of how strongly atoms attract the electrons shared between atoms inside molecules. That's an important concept. Okay, inside a molecule, inside a chemical bond. All right, higher its electronegativity, the more it attracts the shared electrons in the molecule. Okay, and we talked about this the other day. Okay, we'll work through a couple of those problems. All right, good. That's your review right there. So vocab, conversions, and any stuff that was done in your homework during this time, make sure you know how to work all of those. Okay, ordering them from big to small, ordering ions versus their neutral atom, converting even something like silly like kilometers to angstroms, or the other way. Okay, you know, moles are not going away, so converting moles to molecules, to grams, or any combo of those. All right, so we've been doing bell ringers on those. We've been doing bell ringers on conversions here. We've been doing bell ringers on density. Okay, so it shouldn't come as a surprise when some of that stuff pops up. All right, we're not just wasting that 10 minutes. We're trying to get you guys conversant with these basic skills. All right, so make sure you guys are brushed up on that. All right, so we're going to do number 15 here, which, what is it? All right, so condensed electron configurations for Cu2+. I think that's arsenic 5+, silver 1+, and gold 3+. All right. So how do we approach these? All right. So first thing is, if we're going to do condensed, what I would do is I would write the regular one. All right. So what do we have? We've got copper. Okay. And so the regular one is what? We do all the number. So we got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. All right. So, and it's condensed. So we're going to go back to the one before, and we're going to write argon. Okay, and we're going to come off of that. 4s2. And remember, guys, if you don't write it correctly like this, 4s2, it's wrong. All right. Now, maybe not all the way wrong, but it's going to be minus a point or more wrong. All right. All right. So 4s2, and remember again, the D shell is one behind, so it's 3D. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. All right. And so we have a 2+ here. So the question is, does it lose out of the D shell or does it lose out of the S shell? And we go back to here and we say, all right, now what were the rules that some person has spent their entire life figuring out? Okay. Electrons an element loses during ionization come from the orbital with the highest principal quantum number n. All right, so we see right here they give us an example. It loses the S and the P to make this 4+ before it loses the D. So that just means we lose the S and the P before. All right, so what do we have? We've got 2+ that we're losing, so we're going to lose the S's here. So this ionizes to argon 3D9. Okay, so that's your answer. And again, I'm not going to require you guys to write the right one, or I mean the non-ionized one, and then show me that. I think it's wise to do that because it helps you think through. All right, it makes you not try to count backwards. You might be tempted to say, oh, 2+, You can't see that. Sorry. You might say 2 plus. Oh, look, it's just 3d7. And then you write it like normal, which is wrong. You need to remember that this is gone. All right. So arsenic. Let's see if we can find that guy. All right. Here we are. Arsenic. 5 plus. So we got a challenge here. All right. We're doing the condensed version. So what do we have? We've got argon. 4s2. 3d10. 4p. 1, 2, 3. Okay, so that's our non-ionized one. So then it ionizes to argon. What? We're losing 5, right? 5 plus means it loses 5 electrons. So 1, 2, 3, 4, 5. Oh, good. That works out. All right. And if we had an additional one that we lose, we would then go down to 3d9. Okay. All right. And remember, one of the other things that you need to keep in mind is that everything is trying to get to the noble gas configuration. Okay. And so when you see a huge jump, like on lithium, we talked about this in the thing the other day, the last time we did lecture. When he loses that first electron, all of a sudden he's got a nice, stable, noble gas configuration as far as his electrons are concerned. Okay? So remember, if we think about this like dollars, he's going to give that first electron up for real cheap. But that second one, he does not want to sell it. All right? So it's 15 times as much, and that's true across the board for all of our elements. All right? So for arsenic, and remember that each ionization energy gets more and more and more because you're getting it further and further away from its ideal, what it wants as far as energy goes, its ideal configuration, I guess. So even when it is going to a noble gas, that's still not the best, because the best is for them to have an equal number of protons and electrons. All right. Back to it. Ag, silver, 1 plus. All right, so we got to do our full one first. We don't have to, but it's best to. All right, so again, where are we? All right, so our noble gas previous is krypton. And what do we have? Krypton, 5s2, 4d, 1, 2, 3, 4, 5, 6, 7, 8, 9. 49. Okay. And we're just Ag+, and again, as it ionizes, we lose it from the higher one first, so that's krypton 5s1 4d9. So again, you should be writing, these should feel wrong to you because our Madelung's rule and our Hund's rule and all that say they fill from the bottom up. And then we know what order they fill in because we kind of beat that into our heads, right, in the other chapters. So these should look wrong. Well, they're wrong because they're ions, okay? So they're not in their happiest state. They've had energy put into them to put them into a less than ideal state. This is their happy state, okay? This is their happy place. And they had a hard day, they go here, all right? Then somebody gives them some energy, and they go here, all right? So this is the ideal base state, all right? Au, which if you guys have ever watched James Bond, Goldfinger, the bad guy's name is, he's obsessed with gold. His name is Auric, A-U-R-I-C, which is actually Latin for gold, which is why this is Au. All right, so we have Auric or gold. His noble gas configuration is going to be based off of xenon, or excuse me, condensed configuration. Xenon what? 6s2. All right, so now these guys are in there. 4f14. I will not ask you to do one of these, by the way, on a test. 5d10. 3, 4. Sorry, not 5D10. 5D 1, 2, 3, 4, 5, 6, 7. 5D 9. Okay, that's our normal one. What's it ionized to? 3+. So what's it going to lose from? Highest number. 6s2 is going to go away. And then, are we going to go to 4? Nope, we're going to go to 5. So this is going to go 5D8. So it's going to be xenon 4F14 5D8. And if that one doesn't follow the rule, I'm not aware of it, but that if it's following the rule that we set up, that's what it should do. Some of these ones in the D and the F, they don't quite follow the rule, okay, because things get a little wonky the more layers of the D's and the F's you get because they interact, okay? But again, I'm not going to ask you to do one of those. Point is, I think the point of this one is to make you think it loses from the 6, then it goes to the 5, and it doesn't touch the 4 until after it would have completely exhausted the 5D there. Okay? All right. 15. All right, we're going to have to step it up here. All right, let's flip over to 17, excuse me. All right. Based on your knowledge of trends, following atoms in order of increasing ionization energy: argon, strontium maybe? Phosphorus, magnesium, barium. All right, let's look at what we're going to consider here to compare these. And remember, we're not actually looking them up. That's not the point. The point's not to get us to just find numbers. Okay? What is it that makes things ionize more or less? Okay? I think argon's going to be the highest. Okay, what are we trying to do in order of increasing ionization energy? I'm going to put argon all the way over here. Why? Because he's in a noble gas configuration and he doesn't want that to change. Okay? And then, what are our other considerations? All right, sorry, I had to find this chart. I didn't want to try and flip around. All right, so let's look at the trends. All right, what else? So we see helium, neon, argon, krypton, xenon. So those are all of our noble gases. They really don't like giving up electrons. Okay, so they have the highest first ionization energies. And then what's the trend? As we move from left to right, they get higher. Okay, because as we're adding protons, they hold those electrons more securely, and he calls that the decreasing the decreasing efficacy of the shield effect. Okay, more protons kind of overcomes the blocking of the other proton. The blocking of the electrons on the other electrons. All right, so we should see that as we move from left to right, we end up. I'm all over the place here, guys. Sorry. All right, let's figure out where everybody is here. Okay, so we have SR. I don't even know where that is. There it is. All right, strontium. Then we've got phosphorus, magnesium, and barium. Okay, so I'm gonna think through this, and I haven't actually done this one yet, so you'll will sympathize with me. All right, so we've got magnesium and barium. Think about the outermost electron and how far it is from the nucleus. Okay, so this outermost electron for magnesium has only the second shell of electrons and the first shell of electrons blocking it. So that's going to have a lot more attraction between protons and electrons than is barium. Okay, and they're both S2 electrons that we're talking about being the outermost electrons. Okay, so I'm going to say that magnesium is ahead of barium. Okay. All right, then let's look at, oh look, there's strontium too. So he's going to be in the middle of those. Okay, so we've got 1, 2, 3 in a row, all S2s, you know, because this is 1S1s, or these are S1s and then S2s. And so they're wanting you to think through comparing these in a vertical group here. Okay, so that's one group here. So we're not sure where this is going to fit. We know we've got our guy over here in the noble gases. He's going to be the highest. Then we got this group in this order somewhere. So who do we have to figure out? All right, the only thing we got to figure out then is where phosphorus comes in. Okay, and compared to these, what do we think about him? Okay, well, what does he say? He said there's a decreasing efficacy of the shield effect. So as we add, so let's talk about just phosphorus and magnesium. Okay, as we go from here to here, what have we done? We've added another proton, another proton, another proton. And we had the same shields, level 2 and level 1 shields, in between these electrons. So I'm thinking that we got more protons, and it's going to be harder. So we're going to put, but so does phosphorus go, oh, yeah, he's harder than magnesium, so he's going to go here. So my final order is barium, strontium, magnesium, phosphorus, argon. All right, we ordered these based on the same electron in the S shell. Of course, different. This is 2s, this is 4s, this is 6s, but they're all S2 shells, and they've got more shield between them. So this guy's going to be easier. And then we compared phosphorus compared to magnesium, and we saw that we're going to have the same shielding of the 2 and the 1 levels, but more protons to hold it in place. And then we know that this argon is going to be the most. Okay, so that's from least ionization to most ionization energy required to remove an electron. Okay, now I'm not going to ask you to try and figure out whether zinc or silver has a higher ionization energy. That's not the point. The point is, know that your noble gases are the most. Know that as we move down, it gets easier to remove electrons, so have a lower ionization energy. And as you go this way, you have an increasing ionization energy. All right, and what do we see? Is that what we see on this chart? Okay. It is what we see on this chart. Okay, so as we go down the chart, it gets easier and easier. So helium, neon, argon, krypton, xenon. It gets less energy, meaning it's easier. And then as we go from lithium to neon, it gets harder and harder. So as we add those protons that lock those electrons more tightly in place, boom, we see that trend. So we see a trend as we move down the periodic table, and then a trend as we move, sorry, that's not very helpful. A trend as we move from left to right. Okay, so again, I don't recommend memorizing it. I recommend you understanding what's going on. Protons hold electrons tightly, and the shielding effect, the less energy levels you've got in between there, the less shielding you have. Okay? All right, so that is that one. Man, we're not speeding it up at all here. And if we run out of time, y'all please go back and watch the rest of this, okay? It's going to help you. All right. Ionization energy and electron affinity. I would just recommend you being able to, like I was saying, one is energy in to remove an electron, and one is adding an electron in and the energy comes out. Okay, understanding that relationship and be able to say something like that. All right. I've already taken too much of y'all's time. All right. Why do chalcogens form ions with a charge of -2? Let's look. All right, so where are our chalcogens? That's these guys right here. Why do they want a -2? Very simple, very straightforward answer that will get you 100 out of 100 points on that question. If I didn't sound right. Get all the points on that question, okay? Atoms want a noble gas configuration. For an oxygen to get a noble gas configuration, what does he need? In his valence electrons, those outer unfilled shells, he needs 1, 2 to get to the noble gas. Okay? Giving him a 2- preferred valence, or an oxidation number, or what was the actual question? He wants to make a 2- ion, basically, is what we're saying. Okay? Yeah, why do they form ions? Because they prefer, if they're going to be ions, they prefer to be neutral. Okay, but if they're not going to be neutral, they want to be ions that have a noble gas. So these are -2s. These are -1s. These are +1s. And these are +2s almost always. Okay? And you just need to know that. All right, very quickly. All right, what's the likely to have the greatest difference between third and fourth ionization energies? How do we know? Chlorine, scandium, sodium, or carbon? Okay. What do we say? Between third and fourth. All right, so we need to know, we need to look for one who's going to have, between its third and fourth, the third would bring it to a noble gas configuration, and the fourth would remove it from that noble gas configuration. So what do we have? I'm looking at scandium here. He's looking the most promising. So what do we have? First ionization. Second ionization. Third ionization brings him to this configuration, which is where he wants to stay. So the fourth will try to remove him from a noble gas, which he doesn't want to do, so you're going to have to pay him a lot of dollars to give up that fourth. Okay? And as we just talked about, this is 4s2 3d1, so he's actually going to lose 1 electron, 2 electrons, then he's going to lose that d electron third, and he's going to be at the noble gas. Okay? So he's the one. Chlorine is going to have a big jump after his first one, but that's going to be between the first and the second, not the third and the fourth. Sodium also is going to be ionized 1, and then he's going to be happy, so there's going to be a big jump between 1 and 2. So again, between the first and the second, between the first and the second. Scandium's the one that's got it between the third and the fourth. Okay, so it wants to get to noble gas. All right, and then is that finally? We have finally yet? No. All right, we're just electronegativity, basically. Most electronegative, least electronegative. We'll have a couple of questions on that. That's the only trend that there is. Okay, most, least. I'm not going to talk too much about that because it's just a sort of a fact. There's not a whole lot of explanation that needs to happen there. And then 28. Why don't noble gases have electronegativity? I'm sorry. Electronegativity values. Okay, because they, first of all, don't like to form compounds, so it's hard to have electronegativity values when you don't form compounds. And then secondly, even when they are forced to form compounds, they don't pull very hard on the electrons because they've got all the electrons they need. Okay, so that's it. They're happy with their electron configuration. All right, guys. Best of luck on the lab. Best of luck on the test. Y'all email me any questions. Y'all group me if you have any questions you think everyone will benefit from and you don't mind me answering on there to the group. And other than that, y'all study hard, look back through your thing, work back through your homeworks. I recommend reworking some of those if you have some time to do that, and understanding why these trends are what they are, and not just trying to cram and forget. All right? All right. Well, I will see you guys. It'll probably be, let's see, we'll have an experiment, so I won't talk to you on Thursday or Tuesday because you got a test. you may have some lecture. We may talk on Tuesday. All right. See y'all soon.